Hello, is my slide visible? Hello. Yeah. So, good evening. So, we will now continue with the next week of our live sessions. So, today we will be going to discuss like Euler's equation, Bernoulli theorem, etc. So, related topics to that. Uh, and we will be solving. I think it should be assignment 7. So, edit it. This is assignment 7. Let's start with the first question. So, first question asks, uh, what is it just asks basically what is Euler's equations of motion for flow of an ideal fluid. So, can you tell me which one is correct? It's a very straightforward question of about the definition of Euler's equation.
Sir, the energy and the flow is implicit.
The uh, uh, the flow is implicit.
Yes, sir, flow is implicit.
Flow is implicit, and which uh, it's a conservation of what? The conservation of it's a conservation of momentum. So basically, what is Euler's equation? Euler's equation is the special type of uh, uh, your force balance equation or the momentum balance equation, uh, where the fluid is considered to be implicit. So the flow is implicit. So, have Navier strokes been covered before this, or like this is like uh, like before you are approaching like a general Navier strokes equation? I want to know that.
No, sir, that is not covered.
Okay, no problem. We can discuss that. So basically, so far, what in fluid mechanics course was what we have learned is how we like interpret our fluids and like what are the different systems of interpretation. So mainly, we have learned about the Eulerian frameworks and the Lagrangian frameworks, and we have learned that the Eulerian framework is more useful for us for like observing different fluid phenomena as like we stick to a particular geometric location and uh, uh, whatever like fluid particles can come and go, but the behavior at a particular region is generally what we are interested in when we are studying fluid mechanics. Let it be in like various applications of like motion of ships or um, aerospace engineering or like in pipe flow or microfluidics. So, most common way of approaching a fluid mechanics uh, problem is by uh, by like using the Eulerian framework. But what we know is that our equation of motion, if we like force balance equation through which we can study the kinetics of any object, is actually the Newton's second law. So Newton's second law, this equation is valid for a point particle, and like so, this is basically a Lagrangian, like in a Lagrangian sense, this is valid. So what we do is basically we convert this to a fluid mechanical sense. So first of in a Eulerian framework, we convert this in an Eulerian framework. So what? we generally have this mass into acceleration. So for mass, we take the density right now, because like when we are doing an in an Eulerian framework, we are not considering individual particles. So we do not have individual particle mass. Rather, we are considering a whole geometry, and since we are working also in continuum, so in that whole domain, what we call as a domain, each and every point will have some density associated with it. So we'll use that density instead of using a mass of a particular particle, because we are now currently doing an Eulerian framework. Now, what about the acceleration? Acceleration, we have done a lot of examples, like how we will describe the Lagrangian acceleration that will be used in our Newton's second law. How we will describe that when we are talking in the Eulerian framework, we will use the material derivative. So we will use the material derivative. So this is this. So what is this equivalent to? This is equivalent to my mass times acceleration. So this portion is equivalent to my mass times acceleration. Hmm. So this is like Eulerian, and this is Lagrangian. And, okay. So what is this? This is for a point mass, a point particle. And what is this? This is for a particular point in a domain of an Eulerian system. Okay, so we are like we have fixed a particular area that we are visualizing, and in that area, for a particular point, what is the acceleration? What is the mass times acceleration associated with this is given by rho into material derivative of the velocity. Okay, is this clear? This part is clear. Hmm. How
Yes,
we
yes.
yeah, how this MA is equivalent to this. Okay. All right. So now what we have, what else is there? We have force, right? We have force for the Eulerian framework. We have force. Lagrangian framework, we have force. We have to find something equivalent to this. Now we have also actually done this. We have also actually done this. So what are the two types of forces acting on a fluid element? We know there are two types. One is the body force, and another is the surface force, right? When we take any small element of fluid, what are the forces acting on? One is the body force, and another is the surface force. So those are the forces that will be acting. So if we take a small point, so this is basically like a point in my continuum sense. So like since when we discussed about continuum, continuum hypothesis, we discussed how how small a point in a continuum means. So if we go very small, then we will approach the water molecules. Then no longer my continuum theorem is valid. So we studied something called a Knudsen number, if you remember. So after a critical Knudsen number, then we can consider it to be continuum. And in that continuum, even if you select a particular point, that particular point will be associated with a large number of water molecules, such that like the system there is like a continuum properties like densities can be assigned to that. So what will be the body force of that in that particular point? So this will be, if it is like suppose if this is proportional, for example, what is the example of a body force? My body force example, one of the example is gravity. It's a very common example. So how the gravity will can be defined? Since that is defined here in my Lagrangian framework, so let's do it one by one. So let's first talk about gravity. So gravity is m into g in my Lagrangian frame. So this, my m I am representing using the density, right? The inertial property I am using representing using density. It will be rho times g. So just this m is replaced by rho. Okay. What about if there were an electrical force? What would have happened? So in electrical force, we know the force is basically the electric field. Whatever electric field is there, plus the charge. So what will be the Eulerian version of it in this particular equation where we are doing it like per unit volume for every point we are finding this equation. So this E will be there, obviously electric field will be there, and instead of charge we will actually do charge density. So this is basically the charge per unit volume, like mass density. This is charge density. So these are examples of body forces, and body forces will actually be represented like this. So for now, we are only like let's like keep our concerns confined to gravity. So we will use this in our equation. If there is any electric field, we can add this. If there is another any other body force, we can use this similar concept to find out the equivalent of Eulerian representation. Okay. Okay. What else is there? The surface force is there. So surface force, where does like all the surface forces come from? Surface forces come from the stresses acting on it, right? On the surface of this like particular small fluid element that we have considered, on the surface of it, what are the forces acting? So those will be the surface forces, and those are all um basically covered under the stresses and the traction forces that are associated with the stresses. So we will like this is basically the traction force. So how that will be represented? That can be represented like this. So this is basically traction force vector, right, on each of the surface. So sigma is the stress tensor. Sigma is stress tensor, and this is the okay. Now if I write all this together, so what will be my this Newton's second law? So my Newton's second law in my Eulerian framework will look like this. This will be rho dV/dt is equal to this uh, plus this is the stress. This is the surface force part, and this is my body force part. Okay. G is also a vector, so I'm putting the vector sign. Is this clear? This part is clear.
Yes, sir.
So this is how many equations is this? This how many equations is this? This is actually three-dimensional equation. If you can see, like each term is actually a vector. Like for example, gravity term is very clear that it is rho into g. So this is basically three equations: gx, gy, and gz. So same thing for each and every term. You will see this is actually three equations. So when we are talking about this kind of equation, we will say equations. We will use a plural for this because these are three equations. If it is a two-dimensional motion, we will have two equations. So these are called Cauchy's equation of motion. Equations. So use this S here. Equations of motion. Okay. Now let me add a page after this. Hmm. So so far what we have arrived at this equation, right? Cauchy's equation of motion. dv dt. This is equal to z dot sigma plus rho g. But have we ever mentioned anything about the fluid? We have not mentioned anything about the fluid so far, right? We have only used two things while coming to this. We have used only two things. One, that this is in Eulerian framework, right? Eulerian framework, and secondly, this follows my continuum hypothesis. right? Have you used anything more than this? No,
No,
right?
sir.
Hmm. So this equation is valid for everything which comes falls under these two assumptions. So this may be this is valid for fluid as well as this is valid for solids. Hmm. So we have not used anything which describes a fluid. So it's the same equation is actually valid for solids as well. Hmm. But we will like for there we are not concerned with the velocities. When we will study solid mechanics, you will see we are more concerned with the like displacement. So this particular equations only we will like derive it in whenever you study solid mechanics, you will see this is done in such a way, but displacement is used instead of velocity. But now we are studying fluid mechanics. So now how to proceed further? How to use that we are actually studying fluid? So one thing that we can actually, one term that we will focus the most on is the stress. And we have already done a lot of with stress. So let me use the IJ notation here. What we have done here, we have said that this, this plus. Can you tell me which, what is P? What is P here? If I break my stress tensor like this, what is P? P is my pressure, right? I think we had covered this in like week, I don't know, week 2 or 3 maybe, when we were studying about this stress tensor. So P is pressure definitely, but which kind of pressure? That's also an important question. So we have two kinds of pressure. One is the thermodynamic pressure and the mechanical pressure. If you revise, you will uh, uh, you can revise like we have already covered this. So this P here, this is the thermodynamic. This is not the mechanical. What is mechanical pressure? Mechanical pressure is basically just taking the trace of this and divided by 3. So mechanical pressure is 1 by 3 sigma K. But that will include the trace of this second term as well. And so this will not be equal to the pressure term only. However, this is the thermodynamic pressure that we generally associate with our like states of matter. Like if we are dealing with uh, gases which are like which can also be will also fall under the fluid category. So there the thermodynamics states matter a lot. Uh, uh, so for example, gaseous states equation, real gas equation. So there you will use this pressure, which is different, which might be different from your mechanical pressure. Okay, what is tau ij?
Stress, sir.
Oh, then what is sigma ij? Sigma ij is stress, right? We are breaking down stress into two components. So this is a special kind of stress. Definitely it's stress, but this is a special kind of stress which is called the deviatory stress tensor. We have already done this. You can revise this. And this is a pressure component. So there are two types, basically, this and this. Okay. Now we can substitute this sigma, the stress, in this my Cauchy's equation. Hmm. And also like this tau ij for fluids, this can be again broken down. So if we substitute just this, let's first let's only focus on this, not complicate it too much. Then if we just use this and substitute here, we will get dV dt. This is equal to minus grad p plus minus grad p is coming from this first term, right? If I take my divergence of this, so delta ij is basically what? This is the canonical delta, right? If, whichever directions you break it down as the components, you will always find the identity matrix as its components. If you take the divergence of that, it just gives 1. So, uh, like this can be reduced to this. Yeah. So, what about tau ij? Tau ij, this will remain. So this is divergence of the Debitory stress tensor. I will just represent it like this plus my rho g, my body force. This equation is my Navier stress. This equation is my Navier-Stokes equation, but actually, like, not really. It's an incomplete form, provided that we substitute the tau value as well. So this tau, as we have already done this, like this is a function of my velocity gradient. So I'm representing using V, so I'll write V here. So Vi xj. So tau is a function of this. So it depends on my velocity gradients. Why? This is basically associated with the viscous stresses. Basically, viscous stresses. The velocity gradients are associated with viscous stresses, and also like the normal increase also, like longitudinal increases also. It is associated with these two things. So these are generally like for a Newtonian fluid, we can write this as mu with j plus del j del xi plus lambda. Are you following? Are you following what we are doing? If there is any confusion, please let me know. Then I will like slow
Yes,
down
sir.
or like go in any other direction. May help. It's all right, right?
Yes, sir.
Okay. So here we have this mu, which is our usual dynamic viscosity, and there is also lambda, which is the volumetric viscosity, which we say. Because this, like from our previous class only, you can understand that this is, um, if we do the velocity gradient tensor, if you write down its components, so this lambda, this is taking the effects of the diagonals of the velocity gradient tensor. And what does the diagonal correspond to? Diagonal corresponds to the linear strains. The linear strains fx is represented by this second term, and its coefficient is lambda. So that's why this is my volumetric viscosity. So the effects of the linear stresses are incorporated. And what about mu? Mu takes the off diagonal velocity gradients. So like for x velocity, if there is x velocity, then and like y directional gradient. So these kind of stresses due to this kind of velocity gradients are uh, taken care by mu. So this is the viscous stresses. So the like shear stresses. So the shear strains are means represented by this, and mu is basically used to represent these shear strains to my shear strain components to my stresses. So if we substitute it in this equation, we'll get the Navier-Stokes, complete Navier-Stokes equation. So here, what are the terms are there? Then we can again like revise what terms are there in the Navier-Stokes equation, because that is most important thing. You do not like always need to solve the whole Navier-Stokes equation mm, as it is. Even like using softwares, you don't need to solve the whole uh, equation as it is. But you can make some simplifying assumptions based on which type of forces will be dominant in the particular area of application that you are working on. So you can make those assumptions. So it's always good to know what are the terms involved. What is the first term? This is the inertial term. This is the inertial term. The rho density is there, so this is basically mass into acceleration. The second one is due to my pressure. This is my pressure term. Second, this one grad dot tau. This has two components. One is my viscous stresses, and second one is volumetric stresses. Overall, this represents my stress terms or deviatory stress term to be very precise. And whatever else other term is there, this is my body force term. So here I have represented gravity, but if some other forces are also there, we can definitely accommodate within this framework. And also this inertial term is comprises of two components. We already know this, like since this is our material derivative, this is comprised of two terms. This del del T, and another is this. So this is my temporal term, temporal derivative, and this is my convective term. Okay. So what does the temporal derivative do? If again, we have to always keep in mind we are working in an Eulerian framework. So when we are looking at a point, there will be fluid particles which are coming in and again like leaving the system. So temporal derivative actually focuses on the velocity variations with time at a specific point in space. So it has nothing to do nothing means this is not my acceleration. So acceleration is the whole thing, but del v del t here is my change in velocity at a particular point in space. And what is convective term? Convective term is like the effects due to the convection part of like a convection of my fluid. So these two, combining these two, consists my inertial term, this first term, and here are these force terms that we have discussed: the pressure term, the stresses, which include the viscous and the volumetric stresses, and the body force. Okay, is it clear? Is everything?
Yes, sir.
If you have any questions, please you can ask me. Okay, no problem in that. Okay, so now let's move to the like thing that is asked here. That is the Euler's equation. So we have till now uh, just talked about my Navier-Stokes point. What happens if I include all the fluid mechanics things? So this is like a generic equation of motion. So we are studying equation of motion here. Like this is force. This is basically a variation of my Newton's second law. So we are only balancing momentum. So here, when the question asks, what is this the principle of conversion of? This is always a principle of conversion of momentum. It has nothing to do with mass or energy at the moment. So for Euler's equation, what we will do? Euler's equation basically says, what if the fluid is inviscid? What if my fluid is inviscid? So, a fluid being inviscid actually does not always relate to my uh, viscosity being split. Hmm. What it actually signifies? It signifies that this deviatoric component of my force is zero. So this means fluid being inviscid here, flow being inviscid rather. Hmm. So you can use flow as well. So here this means this gradient divergence of this deviatoric stress tensor, this is equal to 0. So if this is 0, my equation of motion simplifies. My equation of motion becomes dv dt. Pressure term will be there, but the deviatoric stress term is not there. And what I will have is I will have my body force term here. So no deviatoric stress tensor. So only stresses that is acting is due to the pressure. Pressure is also stress you should always keep in mind. So only stresses that are acting are due to pressure. No deviatoric stresses or effects of fluid velocity gradients is not there. Okay. So let's come back to this question again. So which one will be the answer of this particular question?
Yes, the momentum and the flow is inviscid.
Yes. So it is momentum and the flow is invisible. So it's a very short explanation is given. So now the same question has been asked for Bernoulli's equation. You can like read this question and try to answer. I will be back in a minute. Okay? Hello. So can you tell me which option like will be correct? So here they are asking what is basically what is Bernoulli's equation. So which of these following options is correct?
So B,
Uh, B. You're taking telling B or D?
second one.
Second one. Okay. Energy is at any point in the flow field and it is obtained by integrating the Euler's equation. Now this is absolutely correct. So we can already see from like we derived the Euler's equation. So this is the Euler's equation. You can already kind of see the three terms of the Bernoulli, right? So how can we arrive at Bernoulli's from here? We will integrate this equation. How? Before that we have to do certain simplifications. So this equation, if I break this first term, this is del v del t plus uh, this is v. So I will put this in bracket v dot grad v. Now what else we have to do for obtaining Bernoulli's equation? Bernoulli's equation is not always valid, right? It is basically comparison between 2 points, but those 2 points must have something in common. And what is that thing?
It should be along the streamline.
It should be along the streamline. That's correct. Hmm. So what we will do, we will consider n cap. Let's say n cap s is a direction which is along a streamline. So this is a vector, unit vector, which is along a streamline, and we will take a dot product with this equation. So, like, we should not forget that this equation is a vector equation. Each of this equation, this Euler equation so far, each of this term is actually three components. Consider like grad p, for example. So this is del p del x, del p del y, del p del z. So all these three equations are written in a compact manner as we are writing right now. When we take a dot product, this is a vector, and each term of this equation is a vector. When we take a dot product, it again converts it back to a scalar form. So we will do that. So this will be del del t, and this is dot v, right? Mm, v dot grad v. This we can readily simplify. What is uh, this? To find out this, we can actually the best way to understand what is this. We can like say, for example, what will happen if ns is equal to I cap, because this is also a unit vector. So it might just as well happen that I cap is actually the direction of the stream. So if it would have been I cap, you see, I cap dot grad. So grad is an operator with three components. So this is like del del x I cap, and there are other three components. So plus del y j cap, and if it is three dimensional, del del z k cap would also be there. It's not required for this example. So I cap dot I cap, this is one, and other components will be zero. So this actually becomes just del del x. So similarly, if it is ns cap dot grad, so this will be equivalent to some del del s, where s is like a coordinate along the direction n. So my pressure, this will just reduce to this. Similarly, my this gravity or the body force term will also feature only the s component of g. When you take the ns cap dot product, you will have any other assumption is there for Bernoulli's equation apart from this being along a streamline.
Inviscid flow.
Inviscid flow is obviously there, but inviscid flow we have already taken, right? Inviscid flow we have already taken while deriving the Euler's equations itself. Anything else?
It should be steady flow, sir. Can we take
Yes.
particular case?
So this should be a steady flow as well. So if we take steady flow, then this term will be absent. We can actually integrate it even if it is not steady, but like that will be a very like another case of Bernoulli's equation, not the popular Bernoulli's equation we know, where like this unsteady term will also be present to accommodate for this. But the general form of Bernoulli's equation that we see is actually in the case where the flow is steady. So this first term will be 0, and the second term actually can be uh, like simplified, and the second term can be written because of this component, if you break down, we can you can like very readily see like this is a vector. This is a vector which has components like u del u del x I cap plus uh, no, it has three components, right? I cap will have three components, so it's a big vector. I'm not writing it down. Yeah. So, like if you simplify, you will see that this actually boils down to this del del. So you can do this exercise. If you have any problem with means breaking this down, let me know. I will help you out with that. Mm. So this will break down as this v square. Okay, and rho is obviously multiplied there everywhere. So rho is there. I'm not putting a vector sign on top of v right now because I'm writing v square, because v square is very well understood as the dot product between v and v. And this is a scalar quantity, it does not need any direction. So we have this, we have this, and we have this. I'm again not writing gs anymore, I'm writing g, and it is understood that g here is the component along this direction. If I integrate this, you can easily understand like how what will I integrate along? I will integrate along S. So it will be integrated around the streamline direction. So when this is integrated, this is like this will very easily be just uh, half rho v square uh, plus p minus rho g. Let's say h is the my integration ds. So h is equal to integration ds. Because this rho and g both are constant, they will come out. And this is equal to a constant. So notice I have taken this these two terms this way. Now you may argue that in our books we have seen plus. So this basically depends on which direction your g is. So generally, like it might be integrated in your plus y direction, which is the vertical direction. So when you take the component, it will actually be minus. So let's do that itself. Let's not deviate from what the common convention is. We will have minus sign here, and we will have plus sign here. Okay. So this is my Bernoulli's equation. Is there any doubt regarding how we like arrived at Bernoulli's equation? So let me do one thing. Let me like summarize the whole thing we have done, like exactly from the starting of Newton's law, so that the whole concept is very clear to you. So again, let me start from the beginning. We have so far what we have done is we have studied our mechanics, and we have understood like how what are the different ways this can be represented, and what are the different ways we can like solve for our basically our fluid motion. So we have understood there are two types of frameworks within which we can operate. One is the Eulerian framework, another is the Lagrangian framework. And uh, we have the velocities in our Eulerian framework. Every analysis that we do in our fluid mechanics is in Eulerian framework. But the problem is the Newton's law, which actually describes our like fundamental uh, kinetic equations, that is in my Lagrangian framework. It describes the motion of a particle. So we have to convert that. So that's why uh, we started this journey, and like MA, this F is equal to MA. So this MA is equivalent will be this. Rho is equivalent of M here, and this is my equivalent of acceleration. What is F? F, we have two components. One is the body force component, one is the surface force component. The body force components, there can be gravity force, there can be electrical forces, there can be any other forces. But but we can say like simply convert it like using this logic. Mg will be rho g if E into Q where Q is charge will become E into rho E where rho E is charge density. So this way we can assign body forces in Eulerian framework. What about surface forces? Surface forces we have studied so far to be like those are accounted by the stresses or the traction forces that are acting. And so traction forces will be represented by this grad dot sigma, where sigma is the total stress. So now we can write our Newton's second law in uh, in this form in our Eulerian framework. Now, from here, what we have done, we have uh, broken down this stress. So, stress can be written like this, where this is the pressure, this is the thermodynamic pressure, not the mechanical pressure, and tau ij is the deviatory stress. Now, this deviatory stress, like if it is a fluid, then this is a function of velocity gradients, and that is basically the definition of fluid. Tau ij, the deviatory stress, being a function of velocity gradients. So it has two components generally. The one is for the this is for the shear stresses. So del u I del xj. This means when we plot the velocity gradient tensor, the non-diagonal velocity gradients are like are the related to the shear strength that is given in this component, and the diagonal elements are given in this component. So this is the second one is associated with linear strength and will dictate the volumetric stresses. So it has these two components, uh, and uh, and also body forces there. So this by breaking down the stress tensor, we are now into our fluid mechanics region. This is the generic Navier-Stokes equation. Now we will simplify from here. How are we simplifying? We are using our assumption that the flow is inviscid. If the flow is inviscid, the deviatory stress component is zero. If this is zero, we arrive at my Euler's equation. Now, what I am doing, I am integrating this whole thing along a streamline when the flow is stable. Okay. So now I think you can like identify this. Now when we are integrating equation, now again like we can come back to the our Newton's second law. So Navier-Stokes is basically Euler's equation, or Navier-Stokes is basically this, right? Now if we are integrating this equation, what we are doing? We are doing f dot dx. Now what is this? This will give me that work done and energy balance, right? So what is my Bernoulli's equation? It's an integration of my force equation. So this will represent energy. So it represents energy and it is formed by integrating all of it. So option B will be the correct answer. Okay. All right. So let's go to the next question. So this is steady two-dimensional velocity field is represented by stream function, and flow is frictionless. 2 points are given. Which of the two statements are correct? Please tell me. So first step will be to find the velocities, right? Can you find the velocities?
Yes, sir.
Okay. So what the velocities will be?
Ax square and 2axy.
So what we will use the definitions of stream function here. So u is del psi del y, right?
Yes, sir.
Hmm. So this is ax square and v is how much? This is minus
Minus.
del psi del x. So this is minus 2ax. That's fine. Now what we have to do, we have to find out whether the first we have to find out whether the flow is irrotational. Hmm. So for irrotational, what we mean by irrotational? If my vorticity is zero, then it is irrotational. So how is the vorticity defined? Vorticity defined as grad cross v. Now since there are only two components are there, we can simply do del u uh, del v del x minus del u del y, right? So
Yes, sir.
find out how much this is. How much is this?
It is not zero vector, sir.
It's not zero, right? What is it?
2ay.
This 2ay minus 2ay. So the second term is zero, but this is there, right? So this is minus 2ay, right? Take care. It's a vector. Okay. So what is the next option? Next option is steady state Bernoulli equation can be used to evaluate pressure difference between points P and Q. So 2 points are given P and Q. So can Bernoulli's equation be used in this case? How will you find that out?
Yes, sir. Can be used.
How?
Um, in one way, in one method, we can directly put the points in the stream function. We will
Yes,
get the same value.
yes. If we have the same value of the stream function, that means they lie on the same streamline. Okay. Yes. So that means steady state Bernoulli equation can be used to evaluate pressure difference. Okay. Uh, it's already given that the flow can be assumed frictionless. Otherwise, we will have additional difficulties where we will have to prove that the non-diagonal elements of my deviatoric stress tensors are zero. Because diagonal it doesn't matter because mostly like Stokes hypothesis we can consider. If Stokes hypothesis is considered, the diagonal elements components are basically neglected. But here, off diagonal will still play a role. If the off diagonal components of the velocity are also zero, then we can also neglect that. But here it's already like mentioned, the flow is frictionless, so you do not have to worry about the velocity variance. Otherwise, you would have to check that. So here, this we already can see that this second option is correct. What are the third and fourth options? Steady state Bernoulli equation can be used to evaluate pressure difference between P and Q since the flow is irrotational. Since this is false, so this option is false. We have already seen. A steady state Bernoulli equation cannot be used to evaluate the pressure difference between this. So this is definitely false. So my correct answer is B. Okay. So they have this, done this exercise here. Any question from this? Any doubt from this question? We'll move to the next one.
Sir,
All right. Yes, definitely. Say,
sir,
yeah. So,
sir, in case if it was not frictionless, then we
mhm,
cannot apply Bernoulli's equation, right?
true.
Okay, sir.
Hmm. So then what you have to check is whether this is wrong, right? Oh, this is wrong. If it is not mentioned explicitly, if the flow is frictionless, then we will have to check this. Now, what would happen, like if you break this down, this grad dot tau ij, you will see mostly it depends on these components, where I is not equal to 0. We can go back a little and we have already done this here. Yeah. So we have broken down this tau ij. It has two components, this and this. Now, if you apply Stokes theorem, so Stokes theorem you may recall where this component is basically eliminated. So Stokes hypothesis, sorry, not theorem, Stokes hypothesis, then this component is eliminated. So only these off diagonal terms are present. So these represents my viscous stresses. So if it is not mentioned whether if this is implicit or not, then you can check whether this components are zero or not. Here there are two such components. One is del u del y, and another is del v del x. Right? And del v del x, we have seen that this is uh, del v del x is non-zero. Del u del y is zero. So uh, this would actually not hold if it was not mentioned that it is flow is assumed because my del v del y del v del x is not zero. Okay, is it clear?
Yes, sir. Since it is mentioned, then that is why it is frictionless.
Yes. Okay.
Okay, sir.
And if it is irrotational, then also you can see like these components, if it is zero, then it becomes irrotational as well. If it is irrotational, then you don't have to worry. Then you can apply your Bernoulli's equation. So for irrotational, the way we have derived, this is for the along the streamline and along the streamline and invisible. For irrotational, some other, we can use a different kind of a derivation that I'm not going through because there is not enough time here. So you can check it out. I think it will be there in your books where you just take this curl of your Navier-Stokes equation. Yeah. So if you take that and you see even if it is irrotational, then you don't have to worry about this English again. Then you can you don't even have to worry about your streamline not doing that. If it is inviscid and irrotational, you don't have to worry about it being along a particular streamline. That's why you can solve problems like you will you would have seen problems like this where there is a tank and there is an orifice here and velocity at this point is you are told to calculate velocity of this point. So A and B, you apply your Bernoulli's theorem, right? The reason you can
Yes,
apply
sir.
this theorem is because this particular flow can be assumed as inviscid and irrotational. So you don't have to worry about finding a streamline along which both this A and B lies, because you don't really know whether A and B lie in the same streamline, but you can still apply this. Okay.
Okay, sir. Thank you, sir.
Okay. Okay. So let's move to this question. Question number 4. Here two manometer readings are given. So basically, you have to find out which one which one will be below and which one will be above. So flow direction is this way. Uh, will the pressure be higher when the diameter is more or when the diameter is less? It's a simple problem of application of your Bernoulli's theorem.
So figure 1 is correct
Figure 1 is correct. Why?
because pressure will be more at the entrance.
Hmm. So you here Bernoulli's theorem is basically P plus uh, uh, half rho v square. This is constant, right? Because body force is not there. So we have a pressure head. We call this pressure head, and this is my velocity. So the total head will be constant. Now, uh, where the velocity is higher? Velocity is higher when the tube is narrower, right? From our continuity equation, we will know that when the cross section is smaller, then my velocity will be higher. If my velocity is higher, my velocity is head is higher. If my velocity head is higher, this will be lower. Pressure head is lower. If pressure head is lower, then like this manometer is correct. So manometer 1 is correct. And if the flow direction is reversed, will the answer change?
No,
So
sir.
it won't change, right? Because still your narrower region will have higher velocity. This is a very simple application of your Bernoulli's theorem, and you have to also use your continuity. So you might think like I have studied continuity like this. From here, how I will get to this. So here also you can basically simplify this and integrate to obtain this. Hmm. No, I'm not doing it. I think you can do this exercise. So basically, like from here, you will arrive at something like this, which you are very familiar with. I'm pretty sure you are very familiar with this. Hmm. So V1 A1 is equal to V2 A2. So, uh, so that the same amount of fluid passes through each cross section. And like even from your logical explanation, this should be correct. Like if you draw a control volume like this, there should not be fluid accumulating inside. So the fluid coming in should be equal to the fluid going out. From there also you can arrive at this. Okay. This explanation will be given. These slides are uploaded. I think you will be able to find them. Okay. Let's go to the next question. Here, consider its velocity field is given. Unit vector normal to the streamline is given. So you have to find the unit vector which is normal to the streamline. This is a very similar to the question, very similar to the question that we solved last week. So please try to attempt. And if there is any problem, you can always ask me about like related to the previous questions and previous topics as well. So uh, how will you approach this problem? So equation of
So should we
streamline. Yes. Tell me.
so should we consider the Euler's equation here?
There is nothing to do with Euler's equation. Euler's equation is basically like relating your velocities with the applied forces. So here velocity is already given. So velocity is not an unknown. So you don't need the Euler's equation, right?
Okay, sir.
So here what you have to basically do, you have to find streamline. So you can like simply do it this way. Uh, what is the basically equation of streamline look like? This, right?
Yes, sir.
Okay. Uh, so you can either solve this equation, find out the equation of a streamline, and then answer this question. Hmm. Or also you can do it in the following way. You already know the slope of the streamline of at this point because slope is dy dx. Correct.
Yes, sir.
Slope is dy dx. So what is this? What is the slope? This is V by U. Hmm. Now, what you need to find, like let's say this point is there, so 1 comma 3, this point is there, and the streamline is somewhere like this. So if you solve this equation explicitly, then you will get this whole equation of this particular curved line, right? But you don't need that. What you actually need, you actually need this this vector, right? This normal vector, normal to the vector, normal to the streamline. Okay. Now, what this dy dx gives you? Dy dx gives you this line, correct?
Yes, sir.
Slope of this line. So you can simply put the values of v and u. So v is minus 2a xy and your u is x square, correct? So this is
Yes, yes.
if you put here 1 comma 3, what will you get?
-6.
Minus 6. So minus 6 is your slope. Of this particular straight line which is tangent to your streamline. So if you want to find the equation of the straight line, this will be this minus 6x plus c. Correct.
Yes, sir.
Hmm. Now you already know like the direction of a normal, like from your school level knowledge, you know the direction of the normal to a straight line is basically like if uh, ax plus by plus c is equal to 0 is your straight line, your direction to normal to a straight line is basically this root over a square plus b square I cap plus b by root over a square. So this is a simpler method, so you don't have to find a streamline. You can easily get your answer from here. So what's your answer? Your answer is basically 6 uh, I cap divided by what is this? 6 square plus 1 square. So that is root over 37 plus j root over 37. So whatever is the value, this is your answer. Which one does it match with? Do you have a calculator in hand? You actually
Sir,
don't.
option A, but sign.
No, well, like you actually don't need to solve. Like even this also, you don't need to find the value because you can see that both of these have same sign, right? This is positive, this is positive, correct? So if you
Yes.
look at the options here, you will say this is minus, this plus, this plus, this is minus, this is minus, this plus. Only this option has both the signs in the same direction. Okay. Now you will say that this is plus. I have got plus. This is, here negative is there. No problem because this is also normal. This is also normal, right? The opposite
Okay,
direction
sir.
is also. So both of these, whether this both are plus or both are minus, both of these options are correct. So option D is the correct answer. Okay, is it clear the way we did this approach this question? So this is
Yes,
basically a
sir.
mathematics question. This is as like nothing to do with the Euler's equation because my velocity field is already given. If my velocity field is already given, all the streamlines I can draw them. Every question related to this streamline, straight line, path line, or whatever else you want to do with the velocity field, everything can be done because you already know the velocity. If you don't know the velocity field, then we will use my Euler's equation. Or your velocity field is given, but you want to know the pressure, then you will use something like Bernoulli's equation or Euler's equation. So yeah. They have used this like this is another. Basically same thing. We have done the same thing. They have like given it in form of a formula, and we have like used like our basic understanding of mathematics. So whichever way suits you. Okay. So it refers to the next question refers to my previous problem, the previous problem itself. So it is asking what is the radius of curvature. So can you find the radius of curvature?
So acceleration, using acceleration, can we do, is it the right way?
In acceleration you can do. Yes. What is basically the concept that you will be using if you are using acceleration?
Centripetal acceleration.
Yes, exactly. So, like the concept is if the acceleration is in a particular direction, so where is the pen? Yeah. So, if the velocity is in one direction, so this is the direction of velocity, and you have a particular direction in which your acceleration is there. Hmm. So, one part of this, let's say, draw it at an angle. So, if this is the acceleration, so one part of this acceleration will actually be used to make the velocity faster, to increase the velocity or decrease the velocity. And what is the normal component of this acceleration is being used? It is used to turn the this particular fluid particle. So this basically the normal acceleration. What this will do? This will try to bend this fluid particle. So whatever the curvature we are seeing in a streamline will be due to this normal acceleration. So you are very much correct. We will use the acceleration. So let me write down the velocity field. V s square minus 2 cap. So what will be the acceleration? Acceleration is basically v dot grad v, right?
Yes, sir.
Okay. Find this out how much this will be. So this is basically u uh, del del x of u plus u del x of v, right? I can plus v del y of u plus v del y of v j.
Is it 2a square x cube, sir?
So 2a square x cube. So let's see, like del u del x is 2ax, and del v del x, this is 2ay minus 2ay. So u is ax square. So this first component is ax square into 2ax. So are you telling acceleration or one particular component of acceleration?
one particular component, sir.
One particular component. Which one?
I component as 2a square x cube.
Uh, I am getting something different. You can see my screen, right?
Yes, sir.
Like, is there any mistake here? I cannot find. I don't seem to get what you are getting. Oh, okay. Sorry. Yeah.
Del u by del y, no,
Mhm.
sir.
Yeah. So I have mixed this. Okay, I will write this. So this is V word. Okay. This is del del x u and v del del y v. Okay. So x component is 2a cube, 2a x cube. Can you repeat what is the x component?
I got 2a square x cube, sir.
2a square x cube, right?
Yes, sir.
X cube. And what is the j component? Can you calculate the j component?
I am getting it as 0,
0.
0.
Okay, let me check it once. V del v del x is minus, which is ax square and minus 2ay. So minus 2a square x square y, right? And v component is again minus 2x and del v del y is x. Uh, I don't seem to get 0 again. Can you check? So there minus minus is plus.
Sir, second term, sir, plus it will get cancelled. V del v by del y.
But here 4 will be there, no? Because v here 2 is there and again 2 is there. So this is a square x square y. 4 is there.
Yes, sir. My mistake, sir. Sorry, sir.
Okay. So let me like write it afresh here. So acceleration what we are getting is 2a square x cube I cap plus 2 a square x square y j cap. Okay, no problem. So we can now find the normal because we have already found the normal direction. So we can find the normal component of acceleration. I'll just this stuff in the cap. And yeah, we can also put our x value. X is 1 and y is 3. So x is 1 and y is 3. So n cap, what was the value of n cap? 6 root 6 by root 37 and 1 by root 37. Okay. This is 2a square into 6 by root 37 plus this is 6a square 6a square into 1 by root 37. So overall this is like how much? 18. 18 by root 37. 18 by root 37 a square. This is my acceleration, right?
Yes, sir.
So this acceleration, let me Okay. So here they have found the acceleration itself. So acceleration I will again write it here 18 by root over 37 a square. Now what this will be? This will be equal to v square by r,
R.
right? V square by r. So v square again we have to find out. So v yeah, I have written here v. So let me find out v square here. So, so v square is basically uh, a square x to the power 4 plus 4a square x square y square. So basically term wise multiplication, right? So this is and if I put 1 comma 3 here, so here the uh, x is 1, y is 3, so y square is 9. So this is 9 into 4, which is 36 plus 1, so 37. So this is 37 a square. Correct.
Yes, sir.
So you can put it here. So what we want is r. R is asked. So v square is uh, 37, right? 37 a square. 37 a square, and this is uh, 18 divided by root 37. Root 37 is this side. A square is there, so a square will cancel, and whatever this value is.
12.5, sir.
12.5. Is it matching? Yeah, 12.5. Option B. Yeah. Okay. You will be able to tackle this question. They have done like a similar method. And they have used a minus here, so this minus is not really necessary. It basically depends on which normal are you using. So we used our positive normal that we had got previously. Our value was negative, then we would have used a negative value. So basically, the formula here for this they have used a minus here. The actual formula would be this: whatever the absolute value of your acceleration, this will be equal to your v square by r. V square is always positive. R will be positive. We want to find like a positive value of radius, and thus the whatever the normal component you are getting, you should take the magnitude of that particular. So you don't have to worry about the negative sign. Okay. So we have one more question. So here the figure is also given to like help you out what is happening. It's kind of like a concentric fluid flow. So radial variation of velocity at the midsection of the 180-degree bend is shown as this. The cross section, uh, the cross section of the bend is square. Okay. Assume the velocity is not a function of z. The pressure difference is between. Uh, okay. So what we have to find out is that the pressure difference between the outside of the inside, this pressure difference we have to find out between the outside and inside of the plane. So first of all, do you understand the question? What is the question trying to say? Like we have a go through the question once and like tell me whether you understand this question. So what is the question trying to say? Well, between which 2 points do we have to find as the pressure difference?
So between the inner radius and outer radius,
Yes, that's correct. So inner radius and outer radius. So whenever you have to find such pressure differences, so first thing that should come to your mind is whether I can apply my Bernoulli's theorem. Can I apply Bernoulli's theorem here? I cannot. Why? This is not along a streamline, first of all, right? And this is not even a inviscid flow. There is no mention of an inviscid flow here. There is inviscid. Is it mentioned?
so
Hmm.
can we take it as like a free vortex flow? And since it is irrotational, can we do it like that? Because it v theta, that formula given, is a free vortex flow.
This one. So yes, v theta is given as a v theta is equal to constant by r. So yes, definitely you can use any formula that you know for the free vortex flow. So what will you use if it is a free vortex flow?
Then we can use Bernoulli's equation. So because it is a rotational flow.
Okay. Yeah. Okay. So this actually does not correspond with the figure. Okay. Figure it is like kind of given as linear. Okay. Yeah, sure. Sure. Definitely a good catch. So since this is V theta is a free vortex flow, this is irrotational. This is irrotational. Good. So you can actually use Bernoulli's theorem, right? So now what is the next problem that we are facing? You can use Bernoulli's theorem, that's for sure. So uh, P1 plus whatever your V1 is by 2. So rho will be there, we can take rho here as well. This is equal to P2 by rho plus V2 square by 2. Problem now arises, you don't know the V1 and V2, right? Even if this rotation, this relation is given, here they are asking if this in terms of your mass flow rate and fluid density and like the geometric parameters. So what do you have to relate this to? You have to relate this V1 and V2 in terms of this mass flow rate and did you understand like what you have to do next?
Do we have to integrate it so by taking
Yes,
the area?
yes, absolutely. Uh, to find out mass flow rate, I'm going to the next step. So to find out the mass flow rate, since mass flow rate needs to be like used here, what we you will do is basically uh, for finding out mass flow rate, what is generally required? Rho into V into dA. Correct. Hmm.
Yes,
Now
sir.
here V will be V theta. So whatever the normal direction to whatever cross section you are taking, the normal velocity needs to be there. Hmm. So and so the normal velocity. So this is V theta. So V theta is some constant by r. Hmm. What is dA? dA, the height is given because this is a square cross section. Here it is mentioned. This the cross section is square. So cross section is square. So the height is actually R2 minus R1, right?
Yes, sir.
So R2 minus R1 is one of the dimensions. So dA, this is like one dimension is R2 minus R1. There no variation is taking place, so I can simply write it down here. And another dimension is your R. So you will write dr. And you will integrate this from R1 to R2. Right?
Sir, one doubt, sir.
Yes, definitely.
Another dimension dr, which you said, is it width?
So basically, let me dA we have to do now. dA we have to do. So dA is my cross section. So my square. This is my square cross section. One direction is your R, right? And another direction is your Z. So there is no variation taking place with respect to Z, right? Hmm. So when we are doing DA, we can actually do something like this. We can take this as my DA because since no like variation is taking place along the Z direction. So whether we divide this Z as well or we don't divide the Z, it does not like make a difference. Okay. Otherwise, you have to actually write dr and dz, and you do a double integration because dA is basically surface integration, right? It's a double integration. So dz integration you can do because nothing depends on z. So basically, whatever is your function, so some function f dr dz. Hmm. So this will be basically equal to your f dr into integration dz. So this is basically your height. You understand? So when we are taking only this portion, this small area, what is this? This is h into dr. So h is basically R2 minus R1. Have I like made this clear? Like, did you understand?
Yes, sir. So the
Hmm.
limits here will be then for dr.
dr the limits will be R1 and R2, R1 and R2, because your inside edge is this R1 and outside is R2, right? So this figure is there. So I am looking at this section. So this section is like a square. Hmm. And if I take this as R direction and this as Z direction, then your like this point is basically this. So this is R2. Okay. The inner radius is R2. So this is R2 and outer radius is R1. This is R1. So this will like change. So this is R1 minus. So this is R1 minus R2 and you will take the integration also from R2 to R1. Okay. So this is
Okay, sir.
hmm, so this is rho K is the proportionality constant K and R1 minus R2 is there, and you integrate dr by r, which is log, right? So you will have natural log R1 by r. This is your m. Now, what you have to actually find from this equation, you have to actually find k. K is m dot by this rho R1 minus R2 and this ln r1 y. Why you have to find k?
To substitute in the Bernoulli's
Yes,
equation.
yes. Hmm. So v1 square is nothing but your k square by r1 square, and v2 is nothing but k square by r2. So please let me know like which option is correct.
So,
Hmm.
getting option A, but B square, should we take R1 minus R2 as B?
Is it coming together? Let's see. So option B, right? So P2 minus P1 I have to calculate. So P2 minus P1. So P2 minus P1 is taken on one side. So you will have uh, rho K square is there, and you will have this 1 by R2 square minus R1 square, right?
So R1 square minus R2 square. So
R1 square minus R2 square. That's correct. R1 square. Okay, so this part is already in this. Uh, so which option were you saying? Option
option A, sir.
option A. Yeah. So this part is there. This part is this part, right?
Yes, sir.
Hmm. So rho k square is should come out to be this. Yeah. So k is this. So squared is rho square. So like in the denominator, rho will be there, and you have this logarithmic square as well here. Yes. So b is basically r1 minus r2. Sure. So let's see what they have done in the solution. So yes, you can see the b is taken as the width. Basically. So this width that we had taken in the z direction, they have taken. So definitely r1 minus r2 is taken as b. So bend is a square, so b is basically r1 minus r2. So option A should be the answer. Yeah. Okay. So they have here used a different method. So like they are using directly from your Euler's equation. So Euler's equation, if you use r theta component, you will get a like theta square by r. But as you said, like we don't need to like start from so early. We can simply use the fact that this is the free vortex, and we can use the Bernoulli theorem. Since it is a free vortex, it will be rotation, and we can use Bernoulli theorem. Okay. So So this was the last question. So do you have any questions from today's topic or any like previous topic? Then we can discuss. Okay, otherwise, we will close this session. If there are no questions, then I will like close the session. Thanks. Thanks for joining. Okay.
Thank you,
See,
sir.
see you then.